Hi everyone, I'm Zoé Jardon and I'm doing a PhD at the Vrije Universiteit Brussel in Belgium in collaboration with the Von Karman Institute for Fluid Dynamics. I'm very happy to participate to the second edition of the ASIAM conference today that unfortunately needs to be held virtually this year. As most of you may know, additive manufactured components are questioned for their fatigue performance and therefore not adopted for safety critical applications so far. Due to the high temperature gradients during the additive manufacturing process, material imperfections and residual stresses that are known to be detrimental for the fatigue performance of the components might be introduced. On the other side, the design freedom of additive manufacturing allows to include functionalities inside the components. And this brings us to the effective structural health monitoring, or ESHM, that has been developed and is patented by the Vrije Universiteit Brussel. And it fully exploits this flexibility offered by the 3D printing process by integrating a smart continuous monitoring technology inside the additively manufactured parts. The system is based on the detection of pressure waves in 3D curved internal channels or capillaries that are represented in red here, that are embedded in fatigue critical regions of the component. The pressure is continuously monitored at the channel extremities by externally mounted pressure sensors that are represented here in blue on the slide. Based on the pressure variations, the system is capable of detecting the presence and finding the location of a fatigue crack. The capillaries are filled with air and are set initially at a very low pressure P1, and after the structure has been loaded, cracks can be initiated and will then propagate through the structure. And if the crack encounters a capillary on its way, a contact arises between the outer higher pressure P2 and the low pressure volume inside the capillary P1. And due to this difference in pressure, the sudden crack capillary contact induces the propagation of pressure waves towards both ends of the capillary, and the sensors can detect the presence of the crack. And thanks to the wave propagation speed V, the location of the crack X1 can also be retrieved. So to discuss the objective of this work, we go back to the title of the presentation. So the goal is to assess the production of a fatigue sample, as you can see here on the slide, a sample of rectangular shape in which the effective structural health monitoring channel, represented in red, needed for the system that I just discussed in the previous slides, is integrated inside sample, and the production of this sample is done by means of hybrid directed energy deposition. Directed energy deposition is one of the most known and widespread technologies of 3D metal printing, characterized by the simultaneous focused thermal energy from the laser and powder delivery. During the process, metal powder particles are carried through the nozzle, represented in orange, by means of a carrier gas, and the high power laser heat source goes through the inner cone of the nozzle and locally initiates a liquid metal melt pool on the workpiece surface, in which the metal powder particles are melted and subsequently fused with the base material and then form a deposited track on the left side if the process direction is to the right, as it is the case here. The shielding gas is then going through the inner nozzle cone and is used to minimize the oxidation of the workpiece surface and to protect the optical system in the nozzle head from any possible damage during the printing process. For the production of the fatigue sample with integrated ESHM system, the Miklat in-house developed hybrid DED machine is used at the VUB, and it is equipped with a 5-axis CNC control and has the particularity to allow the combination of and the fast change between DED additive deposition on the left side and subtractive drilling milling operations on the right side. 316L stainless steel particles are used of a diameter of 45 to 106 micrometer. The nozzle is a coaxial powder nozzle of Harald Pickler Heino, Argon is used as carrier and shielding gas, and the laser is a red power cube fiber laser. And finally, the laser spot size is about 1.66 millimeter. The generation of the machining trajectories and associated G-codes is performed using MATLAB, and the code asks for the sample geometry, the capillary diameter, and the capillary position as inputs, and generates the corresponding trajectory depending on the chosen print parameters, such as the melt pool diameter, the overlap, and the layer thickness. A vertical build direction is adopted to allow the integration of the capillary. And the capillary is a rectilinear and cylindrical cavity that needs to be integrated in the tensile stress zone of the sample. It's also important to not include it too close to the capillary walls to not induce too high tensile stresses at that location. Therefore, it's chosen to integrate it at 6 millimeters from the sample edge that is located here. Different colors indicate different layers that are printed, and you can see the followed trajectory here. And the yellow trajectories are the trajectories where the laser off condition applies. For the three cases, print of the sample starts with the contour and then proceeds with the infill. And to minimize the introduction of thermal stresses due to non-uniform cooling rates and to enhance the geometrical precision, the contour starting point of the next layer is chosen at the next clockwise sample edge with respect to the previous layer. So switch like this. And on top of that, the infill scanning direction of each next layer is also rotated 90 degrees with respect to the previous one. The first strategy consists of subsequently printing the sample as a full solid, neglecting the capillary, over a number n of layers. Flatten the top surface and remove surface roughness by milling the top surface of that n layer sample. Then the contours of the sample are also milled, and finally the capillary is drilled through that n layer build. This sequence of operation that you can see here is then repeated till reaching the final desired sample height. For the second strategy, the capillary is part of the print trajectory by not applying the infill over the capillary cross-section, and the trajectory starts with both outer sample and inner capillary contours and then proceeds with the infill that is prioritized on one side of the capillary, as you can see here. And then the third strategy relies on a line-by-line infill, switching from one side of the capillary to the other one. And so it travels over the capillary cross-section in a laser off condition. The next step is to find optimal process parameters for the production of the samples. Therefore, initial tests were performed for different capillary diameters, and by considering the overlap and without considering the overlap, for one single layer and for 5 layers on top of each other. The standoff distance was chosen at 8 millimeter and the carrier and shielding volumetric flow rate at 3.5 and 3 normal liter per minute. And it was observed during the printing that higher powder mass flow rates resulted in a splatter phenomenon, as you can see here, and higher laser powers and powder mass flow rates tended to fill up the inner circle of the capillary. And this phenomenon was more important for smaller capillary diameters and for higher deposition heights. And therefore, capillary diameter of 3 millimeter was chosen for the further tests. It's also important to have a not too small capillary to make the drilling possible, and 3 millimeter is still acceptable to not affect the structural integrity of the sample. Further, 30 samples with different parameter combination have been printed, and their print process and resulting geometry was analyzed. And here you have some images of the prints of these samples. And this was needed to find the optimal parameter combination, and the tested ranges are shown here. It was important to find an optimal value for laser power, powder mass flow rate, layer thickness, and overlap. During these tests, it came out that these 4 parameters are affecting a lot the geometry and are closely related. Here you have the optimal parameters that were chosen for the production of the sample. It was observed from these images that there is a need of laser power control to respect geometrical accuracy, and therefore the laser power was adjusted from 600 watt to 360 watts by diminishing the laser power of 10% per layer and of 10% on the contour with respect to the infill. The powder mass flow rate is 3.9 gram per minute, the layer thickness 0.6 millimeter, and the overlap 48%. These are the final hybrid DED samples. The two first ones were produced with strategy 1 and the third one with strategy 2. And the measured capillary diameters were between 3.22 and 3.23 millimeter. The red lines on the figures highlight the transition between one sequence and another. So one sequence being the printing, the milling of the contour, the milling of the top surface, the drilling of the capillary, and then the repetition of the next sequence. These are images acquired during the production of these samples. So these represent the beginning of the second sequence, where you can see the presence of the drilled capillary hole here. So finally, let's take a look at the channel finish and the surface roughness. So the low inner surface capillary roughness is required to avoid undesired fatigue crack initiation triggered by near surface defects, such as pores, lack of fusion, scratches, voids, imperfections, and so on. But it's also important to minimize the influence on the propagation velocity of the waves through the channels that is known to influence the crack localization accuracy. And therefore, a SEM and optical micrograph analysis were conducted, and the study is shown here. So if we take a look at the top view of the samples, we can see clear drilled capillary holes for the two samples with the first strategy. And if strategy 2 is used, a less clear defined contour of the capillary is observed. Now, if we take a look at the front view obtained with the optical microscope, we can see that there is a color difference at the transition between the sequences, and that for the second case here that was printed with a slightly higher laser power, we have unmolten particles that flew into the capillary hole during the printing of the second sequence and stick to the surface of the capillary. Now, this is important because it increases the surface roughness and can initiate crack nucleation. Now, the use of an ultrasonic cleaner together with compressed air through the channel allow to get rid of these particles, and that can be seen here on the SEM images, that to clear capillaries without particles were obtained at the end. Now, the third sample, where for the second sequence strategy number 2 was used, we can observe that the surface roughness exhibits a very poor finish due to the unmolten particles that can be seen here. And the strategy is therefore not recommended with the settings that were used, at least. The drilling of the capillary through the fully printed sample, so with strategy 1, resulted in subsequently lower an improvement of the capillary roughness compared to strategy 2, and is therefore recommended for the build of such a sample. Then multi-focus depth images has been taken and the roughness profiles has been extracted and are shown in the graphs here for the capillary surface, but also for the transition between the milled surface and the printed surface. As expected, if we take a look at the arithmetical mean deviation and total roughness height, the milled surface exhibits lower roughness than the printed one, and the capillary surface roughness gives us acceptable values and will therefore not influence the ASHM system or the fatigue crack initiation. Finally, we can conclude that a clear reduction in the capillary surface roughness has been achieved by deploying this hybrid DED for the production. And we can say that for small diameters, the internal surface quality is too low, and the loss of material is negligible, so strategy 1 should be used. And as a practical recommendation, we should omit inclusions of features with diameters smaller than 4 millimeters and integrate them with these subtractive operations. If a good laser power control is present, the inclusion of features from 3 to 4 millimeter might be possible. And finally, for larger capillaries, larger than 4 millimeters, the second and third strategy are recommended, combined with a surface post-processing such as chemical etching.